Effort to do a lunar probe back around, that would have been 88, 89, somewhere in there. And after we had, after the group as a whole had done a lot of work, done preliminary work, done a full-up design with a small sat manufacturer, and tried to get some private funding, that private funding just didn't work out. And Dr. Binder still kept the faith. He kept the documents lying about in his office and kept looking around for funding opportunities. He is a study in what persistence can get you, and saw an opportunity to submit to the Lunar Prospector as a proposal for a NASA program, and now we have a Lunar Prospector in orbit around the moon. So, Dr. Binder.
Well, thank you, Gay. First of all, I'd like to thank a lot of people in this room. Gay, Peter, I don't say Rick, but clearly, as everyone I hope knows, Lunar Prospector began external to NASA. I like to call it a grassroots effort, which it certainly was. And I try to make a point of that every time I talk to the news media and reporters of any kind, because I feel this is our mission. I do not consider it a NASA mission, which makes me very popular, of course, at headquarters. I'm not popular there anyway. In any case, this truly is your mission. Those of you who, of course, spent a lot of time and effort in the late 80s and early 90s trying to make this a reality, share in this triumph, actually, because this is the first time that a mission has been developed outside of NASA. Gay will remember that we had a series of objectives, and I am pleased to see that with the exception of one, we have met them all. We had our original view graphs a long time ago that said we wanted to demonstrate the utility of small spacecrafts for doing lunar and planetary exploration. We've certainly done that. We wanted to show that it could be done for low cost and in a short time frame. Now the low cost, I don't know how many of you know it, but Lunar Prospector with launch, with everything, is $63 million, which is about 1/10 what a mission of equivalent quality at NASA would have cost. We didn't hit our goal of doing it quickly. It took a long time to find the right support. And that was the one thing that we failed in. We did want to do it using private funding and private support and take it completely out of the government arena, but after 6 years of attempting to do so, the opportunity, which of course resulted in a successful mission, came by with the Discovery program. And we did what I said was the last thing I would ever consider doing, and that's going to NASA and become part of a NASA program. Beyond that, I believe Lunar Prospector has done another of our objectives, and that's created interest in the American public for going back to the moon, to get man back on the moon, get a lunar base started in a lunar colony. And those are favorite themes that I discuss whenever I'm giving speeches to anyone. It also has done something, and Jim Benson is an example of this, and I hope that I will be very soon at LunaCorp. Lunar Prospector did demonstrate that you could do this commercially, and that was one of the big things we wanted to prove, that we could get the cost down and prove that you could use existing technology so that this could become a normal commercial venture. We always say, when we discuss this with the public media, that Lunar Prospector cost 1/3 the cost of the Titanic movie. And so we are now in the regime where this can be done commercially. And everyone knows, I believe, that Jim is making great progress with NEAP. And I'm obviously still flying the mission and busy with that, but I am beginning to worry about Prospectors 2, 3, and 4 and a series of landers. So we have opened the door now with Lunar Prospector to commercial exploration of the moon and the near-Earth asteroids, which is, of course, the beginning of the commercial exploration of the rest of the solar system. So I would like to congratulate everyone in this room who participated, who supported. This is your triumph. I'm pleased to be the one who led it, of course, but I really have always considered this to be our mission, not NASA's, and I congratulate you all for thinking about this, worrying about this, supporting it. Some of you gave money, some of you gave a lot of time, and we all triumphed. So thank you very much.
Did
everyone hear me without that because I will be showing the slides? No. All right, well, I'm just going to move this closer then. Oh, that's brilliant. See?
NASA never thought of that.
Don't get me started on NASA. No questions about NASA. Okay, can everyone sort of see? And if you can, if you want to stick it up, broke it.
Wireless?
Oh, there we go. That's perfect. Yes, magic what you can do with technology. Okay, those of you who know the history of Prospector, I want to make sure everybody can see these slides. Am I out of the way, pretty much? Okay, this is Lunar Prospector. My introductory slide, I want to show you another picture of this a little later, which is the same thing. This is Lunar Prospector in the final stage of testing. This is in the acoustical chamber. Prospector is this. This is the casing for the translunar injection stage, which was a Star 37 engine. And I am extremely pleased and proud to say that when we originally designed Prospector nearly 8 years ago with our Phase B design study, which was done by Omni Systems, it looked pretty much like this. I basically flew the spacecraft that we had designed 9 years ago. In fact, there's a lesson to be learned there. One of the reasons I was able to keep the cost down, even going to Lockheed, which I had to get become part of the Discovery program, the payload never changed, the basic spacecraft never changed. I kept the engineers from adding on, and so what we designed 8 years ago is what we flew, with the exception that going to Lockheed meant that we had to change technologies and go from aluminum to graphite epoxy and things like that. But the key to keeping the spacecraft's cost down is not to let it change. Once you do that, you lose control. In any case, Prospector's goals were defined in the very beginning of the program. And when we started this, of course, we knew at best we would have few resources in terms of money, etc. And so I had picked the payload to consist of those experiments or mapping techniques which could be done from a simple spin stabilized spacecraft that required no pointing, no sequencing, had low mass, low power requirements, low data rates, etc. There still is, of course, a list of orbital and surface objectives that the LEXWIG, the Lunar Exploration Science Working Group, had put together at the end of Apollo, and of course those objectives are still valid today. And so I simply selected those 5 techniques that we thought we could fly on our simple mission, and that was 5 out of about 15, so there's still room for Prospector 2, 3, and 4. And what we came up with then was the gamma ray measurements to measure the composition of the lunar surface. All these things that were twofold. There was always the science component and then the resource utilization component. Of course, as many of you know, we called it Lunar Prospector to point out this was not just science, this was trying to go and prospect. We were going to measure the magnetic fields, use the tracking data to map the gravity field. Of course, the public interest and the operational interest was on the search for polar ice. Now, this is not a high priority science objective because the ice is not lunar ice, it's ice brought there, if it is ice, and I'll discuss that later, by comets and meteorites. And so it's been brought there from elsewhere in the solar system. There's relatively little science information in that, but of course water is critical to the development of a lunar base and a lunar colony, and so it has high interest in the American public and the world at large. And then we were going to use an alpha particle spectrometer to search for lunar outgassing, which had been documented in the Apollo 15 and 16 missions. The basic mission, which we always had, was a 1-year nominal mission, 100-kilometer circular polar orbit. I have an extended mission, which will start in January, where we will drop down, not as it says on this slide, we've been evaluating this as we learn about the gravity field, but to drop down to a circular orbit, 25 kilometers, and map the moon again at higher resolution, higher sensitivity. And my goal with Prospector, even though I'm a scientist and I'm very interested in the moon, etc., was never to do science. It was to prove that you could do things, as NASA calls it, we call it other things, but the meaning is the same: faster, better, cheaper. and Prospector has demonstrated that. Very briefly, I don't want to spend too much time on this. Gamma ray spectrometer is mapping the composition of the surface of the moon, looking for uranium, thorium, potassium, which is an important series of trace elements. And of course, the major elements from here over, those 7 elements make up about 99% of lunar materials. They do also on the Earth, so there's a great deal of commonality there. These are the things that we are going to build our lunar civilization out of. And they're the same things you built this civilization of. There's aluminum, there's iron, there's minerals, etc., which are common to both planets, and that's what we will use to advance our society. A lot of good science, and I don't want to spend much time on that. The neutron spectrometer, which was the second instrument, was designed to look for hydrogen. Now, I'd like to make it very clear. When we say we have found water, you always have to put quotation marks around that because we map hydrogen. Now, we'll show you the results later. We infer water. Now, that's the logical inference, but it's not clear-cut. And as I have always said in all my talks, we map hydrogen, we infer water. You have to go down to the surface to find out what it really is. So make no mistake about that. I will use the word water, and you must remember I'm also saying water ice because it's frozen or it wouldn't be there at all. The third spectrometer is the alpha particle spectrometer, and we are looking for gas release events, and we are looking for alphas from radon and polonium. Radon is a gas, has a half-life of 3.8 days as it decays. When we see radon alphas, we are looking at a active vent. Gases are coming out of the moon. Polonium is farther down the decay chain. An intermediate decay product is a lead, which has a 21-year half-life. And so when we see alphas from polonium, we are actually mapping activity over the last half a century. This experiment is being compromised because the sun is getting very active and we're seeing orders of magnitude more solar alphas, and I'll get to that a little later. The importance of this for resources is simple. The radon is not being washed out of the moon by itself. It's in too small a quantity. It has to be carried out by larger quantities of probably nitrogen, carbon dioxide, or carbon monoxide. Resources which we, of course, very much need for the development of a lunar base and a lunar colony, since 80% of our atmosphere is nitrogen, and plants like to grow in carbon dioxide atmospheres. The magnetometer and the electron reflectometer work together to map the magnetic fields of the moon. The magnetic fields of the moon are very small. We do not have a dipole field. We sit in a 35,000 nanotesla field here. That's a relatively weak field, but nevertheless, that's what we use when we use our compasses. The fields we're looking at the moon are a few hundreds of nanoteslas at best, and they're local in nature. It's caused by the rocks have been magnetized, and we're seeing the magnetic signature of these rocks. The question is, why are the rocks magnetized? And that's what we hope to understand. Again, a lot of science. Also on the Earth, magnetic mapping is a very useful geophysical tool for searching for resources, and of course we always have that as part of our objective. Mapping the gravity field of the moon also gives us information about the crustal structure, about the size of the lunar core, etc. But more importantly, no one had ever been in low polar orbit before, and so we did not know the gravity field of the moon well. And as I will show you when I get to the science evaluation part of the talk, when I designed the fuel load, there was a great uncertainty in how much fuel I would need during the orbital phases. And I multiplied by a factor of 3 just to be on the safe side. And so I'm carrying more fuel than I really need. We now know that the models we were using were very close, but as I show you later in a slide, the dispersion was tremendous, and so we could not be sure. Happily, that gives me plenty of fuel for the low altitude mapping, so I had another plan anyway. This has been accomplished, and the lunar gravity data model now exists, and everyone who follows Lunar Prospector, including, I hope, my own missions, can now properly calculate their fuel loads. Lunar Prospector is a stupid, simple spacecraft. Gay showed one of the slides we had in the very beginning, and it said, keep it simple. And this is the KISS principle, which is keep it simple, stupid. The technology we're using is 30 years old. Everything that I flew on Prospector had been in space before. This is all proven technology, no development. Jim coined the phrase, and I love it, everybody does, Jim, that we are using trailing edge technology. And this is the key to Prospector. It is a single steering spacecraft. There's no redundancy. We built Lunar Prospector. There's one of them. We had, with the exception of the command and data handling unit, we built one of everything, tested one of everything, and flew it. And usually in any NASA program, you have a test model that you build because you test to the limits. We did not test to the limits. So it's amazing that we did this, but again, it's a tribute to using stuff that's already flown and you know the quality of the equipment. My favorite story about the development is that when we went into thermal vac testing, now thermal vac, I'm sure most of you know, is where you stick the spacecraft in a huge chamber. In fact, our chamber was 65 by 85 feet long, so Prospector was a little bump in the floor. It was built for huge military satellites, which Lockheed builds all kinds of secret stuff. In any case, we had a 10-day test cycle, and it is characteristic that you have to come out of thermal vac at least once to fix whatever's wrong. And so we asked for the chamber for 3 weeks, figuring we'd at least need twice as much time as we planned. And so we went at it that way. We closed this huge 65-foot door, pumped down, which took a full day. 7 days later, we opened the door with a perfectly functioning spacecraft. And at that point, I knew that the things that I had believed in, that the simple satellite with the minimum of everything worked. And that's the way the whole program went. We were on time, on budget, all the time, because there was simply very little that could go wrong in this spacecraft. Now, a couple of data about Prospector. It's a small spacecraft. It's 1.4 meters in diameter, about this big. The basic drum, solar drum, is about 1.3 meters tall. You would easily sit on that table. The antennas stick up another meter. There are 3 booms, which I had to deploy, one carrying the magnetics experiment. The spacecraft, given that we are measuring magnetic fields down to 1/10 of a nanotesla, and the solar wind field in which the moon is embedded is about 10 nanotesla. As you can imagine, we had to have a magnetically clean spacecraft. We were very careful about that in the way we wired it. All tools that went near the spacecraft were demagnetized. You couldn't wear your watch near it, etc. When you have one of the more magnetically cleanest spacecrafts ever built. But nevertheless, the magnetometer is sensitive to its own electronics. And so it was put on a little boom extension to keep it away from its own electronics. So that's the basic structure. The panels, solar panels are on the outside. The internal structure has the 5 boxes. There's just 3 main electronics boxes: the battery, the transponder, and the command and data handling unit, which is not even a computer. This spacecraft is ground controlled. I run it from Ames Research Center with 4 people, 3 more people. We monitor it 24 hours a day, but in terms of command and control, there's just 4 of us that run the spacecraft. So that's what it looked like. The mass at launch, and interestingly enough, Gabe, you remember what the Omni estimate of the mass was in their study? 299 kilograms. My launch mass was 296. Now it's a little bit unfair because I had changed the design. We went from a biprop to a monoprop, and there were other changes. So it was, I'm comparing apples and oranges a little. But the point is that I had frozen the design in the beginning of phase CD at about a dry mass of about 148 kilograms, a launch mass of about 182, I believe. And our mass properties guy, the guy who tracks the mass of the spacecraft, swore up and down, hey, and he showed me graph after graph after graph. Spacecraft grow by 30 to 50% in their mass between the beginning of construction and end. And I said, it ain't gonna happen. We grew less than 5%, less than 10 kilograms. You just have to do it this way. Needless to say, I had many good-natured battles with the engineers and happily won them all. But in any case, the spacecraft was almost identical to what we had planned those 8 or 9 years ago. And I'm very, very pleased and very proud of that. This is the picture I showed you before. I hope you can appreciate it a little more. The 2 antenna, Omni antenna, medium gain antenna. You can see the magnetometer, the boom extension, the electron reflectometer. That red cap, of course, is taken off during flight. Their electronics, the gamma ray spectrometer, and the neutron and alpha particle spectrometers are the third booms. You can see the little engines. We had 6 of them. They were 22 Newton engines, or 5-pound engines. The maximum thrust the Prospector has, firing two engines, the lower engines is what I use, for example, to put us in lunar orbit, was only 2% of a G. Very, very low acceleration. You can see the scale with the technician. We house wired and house plumbed the spacecraft. That is, instead of doing what they usually do by laying out big racks of wire and then plugging in the spacecraft, we actually wired everything on the spacecraft. We did everything the way you usually don't do it, and it worked. All of this was done to keep the cost down and maintain the schedule. From beginning of CD to end of it was 22 months. We then had to wait 4 months for the rocket because it didn't catch up. This was the first flight of an Athena 2. It was the first use of the Spaceport, Florida launch pad. Day after Thanksgiving of last year, I went to the Cape. I came back the day of Christmas. My wife is very patient sitting there. In any case, we processed Lunar Prospector. Simplicity is the key. We were 3 days ahead in the processing of this spacecraft. We were always ahead of time because everything that was planned, they were planning it based on previous experience. We allowed for contingency time. We never used any contingency time. We were always done ahead of time. We had planned the fueling of the spacecraft, putting 138 kilograms of hydrazine, which is very nasty stuff and has to be done in protective suits and behind barriers and all kinds of stuff. We had planned a full day to load the spacecraft. It took us 4 hours. And again, we chose a very simple technique. The propulsion system we have is a simple blow-down system, in which it's a monopropellant hydrazine. We have helium pressurant, which was already in the tanks at about 120 psi. We slowly pumped the fuel in, and it had to go into all 3 tanks very uniformly, or the spacecraft would not have been balanced. Remember, this is a spinner, and so it had to be perfectly balanced. We slowly flowed the fuel in over 4 hours. The fueling went perfectly. It was a perfectly balanced spacecraft, and we were done. And that was it. We were ahead of time. The last time I saw a Prospector, so to speak, was when we encapsulated at about midnight, the night we took the spacecraft from the processing facility out to the Cape. And it was a very magical, wonderful moment as we lowered the shroud over the spacecraft, and that was the last time I actually saw a Prospector as a full entity. There were doors because we had to have access to things, and you could kind of look in it. But nevertheless, after having worked on this spacecraft for many years, and of course starting to build it, and I did help build it physically, screwing things on it, testing it. I was a part of every single phase of this, but to see the spacecraft for the last time was a very, very interesting time. I then came home because, as most of you know, I fly the spacecraft and was not at the launch. Some of them in this room were there. My wife was there. The launch was scheduled for the night of the 5th of January. We got within a half hour of launch, and it's an on-time launch. We had to have an on-time launch with the first time spacecraft, with the first time use of a launch pad. And one of the radars went down. One of the safety range radars went down, so we were scrubbed. Actually, I was not unhappy about this because the next night, unbeknownst to anybody but me, was a better night for launch. But I wanted to get launched because we only had 2 days a month, and we only had trajectories for 2 months, and they're $250,000 per trajectory, and we had no more money. The next night, the countdown went perfect, except there was a huge thunderstorm heading right for pad 46. It decided to stop about 40 miles away to sit there, and exactly on time, there was a brilliant little light starting at the bottom of the rocket, and frankly, that's all I cared. Now, this is going to sound strange, but given where we were, the difficulty of doing this, the fact that discovery programs, you can't go over budget, etc. If it was going to go in the drink, it was going to go in the drink, no matter what. If it was going to be successful, it would fly. And I wanted to see that light down there because one way or another, either I was going to go to the moon or the program was over. Happily, it went to the moon. As Bill, the co-investigator who built the 3 spectrometers, said about the neutron spectrometer, we were going to discover water either on the moon or on the Earth. Happily, we did it on the moon. Prospector was launched by Athena 2, put into a 185 kilometer or 100 nautical mile parking orbit. We coasted halfway around the Earth over the northwest coast of Australia, out of sight, out of mind to a certain extent, completely automatic. A timer on the translunar injection stage was started when it separated from the orbit adjustment module of the Athena 2, and an automatic sequence started. We were separated. Half a second later, the rocket spun us up to 51 RPMs. 20 seconds later, the main engine fired. This was all in the blind, and all I could do was wait to see if I would hear Prospector be turned on some 1 minute later. The burn occurred. At the end of the burn, Prospector was turned on, the separation occurred, and I was on my way. I don't have the time in this session to tell you the great deal of fun we had for the first 9 hours. I will simply say that we were supposed to be tracked by TDRS as an experiment, since I would not rise over Goldstone for 22 minutes, because you kind of like to know if you have a live spacecraft and if it's on the right velocity vector. TDRS heard us, so I knew I had a live spacecraft, but they couldn't pick us up because they were sweeping with too narrow a sweep. They finally started picking us up after we gave them the DSN, but I was at 300 bits per second rather than the 3.6 kilobits per second, which is our engineering and science data downlink, and we kept getting dropouts. This was a mistake. We should never have gone to 300 bits, but hey, you make mistakes. And so we did not have a good link, and since the first maneuvers that I was doing was firing the engines to reorient the spacecraft and de-spin it in preparation for boom deployment, I'll be damned if I was going to fire the engines not knowing what was happening with that spacecraft. So we waited out for about 2 hours and sent some dummy commands up and found that we were communicating properly and went ahead and did the reor, and after that, as they say, it's all history. During the first 9 hours, when I took command control of the spacecraft, we did the reors, we did the de-spins, etc. We deployed the booms, which was a critical event. If that wouldn't have happened, the mission would have been over basically then. I turned on the science instruments. We were getting magnetometry data and alpha particle spectrometer data. The other 3 instruments, the gamma ray neutron spectrometers and the electron reflectometer, have high voltage supplies. You have to let them degas for a day, otherwise they would arc and be destroyed. So they were going to be turned on fully the next day. We did our first mid-course maneuver 4 hours late because of the delays I was just mentioning. This was a 60 meter per second burn, and let's see, about 7 in the morning we went, we finished the operations and went to bed. It's a long day, as you can imagine, knowing that the spacecraft was fully functional, the instruments were on, with the exception of the high voltage. We were on a trajectory which was definitely going to take us to the moon, and the spacecraft was happy and healthy. 24 hours after launch, we came in again at about midnight. I started the turn-on sequence to step up to high voltages to the other 3 instruments. They were fine. We did a second mid-course maneuver, about a 10 meter per second burn, and then we shut down. It didn't shut down because the spacecraft is monitored all the time, but my command crew and I left. We had a third mid-course maneuver planned, but after the second mid-course maneuver, our velocity errors were about 10 centimeters per second, and our arrival time was off by 15 seconds, and so it was not required to do anything but just go back to bed. So we let Prospector go to the moon, collect calibration data on the way to the moon, and then 105 hours after translunar injection, we reached the moon, and we did a 32-minute burn to put us into a 12-hour capture orbit. Our actual period was 11.66 hours. 24 hours later, after tracking, we did the second burn to put us into an intermediate orbit, which was supposed to be 3.5 hours. It was 3.55. And then the third burn occurred a day later. We burned down almost to a circular orbit that we wanted. Now, I have to grump at the engineers. My engineers turned chicken on me. I was going to burn down circular, and they were all concerned that we could have an overburn, which engines tend to burn cold and you don't get an overburn. But they wanted to burn light so that we wouldn't crash, and I compromised and said we'd do a 3% underburn. So that put us in a 90 by 150 kilometer preliminary mapping orbit. The nice thing was that we could go to bed. We could change our schedule from working from 12 till 6 in the morning to working normal hours, and we scheduled then the circularization burn 2 days later. We had sufficient tracking to know what we were doing and get rested and get ready for the actual mapping mission. Our circularization burn put us in a 99.15 by 100.3 kilometer circular orbit, which very quickly became elliptical. But it was clear that we could control the spacecraft. It was doing what it was supposed to do. The instruments were working fine, and we were then off doing our science. Now, and since then, about once every 56 days, we do an orbital maintenance burn. We do little tweaks to reorient the spacecraft, and we correct the spin, because when you do a burn, the engines are not completely balanced, and so as a result, you always spin up or spin down. In actuality, every pair of engines we fire burns us and spins us up. Now, how much time do I have left, by the way? 5 minutes. We're going to do science fast. The first thing, as I said, was that we didn't know how much fuel to have on board. These are the pre-Prospector models showing how quickly your altitude of your pericell, the low point, drops down. You see, in some models you hit the moon in 40 days, others you would be pretty good. This is the model I used. The black is Prospector. We now know how to fly lunar missions. That was the first thing. That was within 2 weeks we knew that. Now, mapping the mass cons and the gravity anomalies was very important for science. This is the quality of the data prior to Prospector. The color is the topography from Clementine, and these contours are gravity contours. This is what Prospector is generating. Now, I should say that to do the gravity mapping, you need 1 millimeter per second accuracy. We're getting 1/10 of a millimeter per second velocity accuracy. This is the same map with Prospector's data, and I don't think I have to say much. You can look at that and see the tremendous leap in the quality of the data.
We need access to the green room. One of the speakers has left their computer in there.
I'd like to show, just have you look at the bottom two. In fact, I'll push this up. These are the first neutron spectra maps, etc., from the moon that have ever been taken. This is the thermal flux of neutrons. It turns out this is very sensitive to iron and titanium content of the soil. And what we saw when we saw this map for the first time is, my gosh, there are the Mare. They are all delineated. Here you see the far side polar, south polar Atkin Basin, Mare Australis, Mare Marginis and Smithy. You can see Nectaris and Chrysium, and of course this kind of blacks out here, so you can see all the detail of the Mare. We have a good technique for mapping iron and titanium distributions. The water question is answered from the epithermal flux. This is an epithermal map, and it's these two black little spots at the poles, which tell us that there's excess hydrogen there, and we believe, of course, that that's probably water. Now, what we have done here is taken great circles from that map that I just showed you and plotted them up. And you can see the sort of background level, which is caused by the 50 to 100 parts per million of hydrogen that are solar wind particles, hydrogen atoms, embedded in the regolith by solar wind. It's these two dips, about 3% dip in the north and a 2% dip in the south, which tell us that there is quote-unquote water ice there. Again, I say we only can measure hydrogen. It's inferred there's water. We need to get on the surface to actually determine if it is water. Now, if it is water, and if it's implanted the way we think it is when comets hit the moon, our measurements go down to about 50 centimeters depth, and we don't know what's below that. If you're talking about 1 meter or 2 of water ice, then we're talking about probably 1 billion metric tons of water. If these are thicker deposits, which they probably are, it could be 10 billion tons, it could be more. So this is not an insignificant amount of water. Now, the gamma ray spectroscopy, which is the most important scientific measurement, although, it's not this versus this is a matter of gradation. All these experiments are very important. Any of you who looked at the gamma ray spectra from Apollos 15 and 16 will know that you saw a continuum, and after much massaging of about 6 months, you saw teeny little bumps which represented these spectral lines. These are raw spectra of the type we get after you integrate for the equivalent of a full year. And you see very well the lines, and you can identify them, the oxygen, the iron, etc. Now, these data are of such high quality that now this is Mare Imbrium, where there's a lot of creep, that is potassium, thorium, etc. I'm going to lay over you this. A Farside Highlands area. And you can just look at this, and you can simply see there's virtually no thorium in the far side and a lot here. The potassium is depressed on the far side. The iron contents are different. So just looking at these spectra, you can see the information is there. So when we get done, we will have very good qualitative maps of the distribution of all the elements that I mentioned earlier. Now, creep, as I mentioned, is a very important trace element material, and this is the first complete map of the moon thorium distribution. You can see this is concentrated around Mare Imbrium. There's a long story about this, but just let me show you the quality of the data. The Apollo 14 landing site in Fra Mauro landed in one of the richest areas. This is the far side polar, South Polar Atkin Basin, and this is the quality of the data we will be producing for each of the different elements we are mapping. This is a 5 by 5 degree grid. The resolution of Prospector for these nuclear detectors is 150 kilometers. It's a big chunk of the moon. It's not real high resolution. The only thing you can do is get lower, and that's what we will do during the extended mission. Similarly, this is an iron map, again at a 5 by 5 degree. We've only been there 4 months, by the way, out of 18. So I think you can understand we're going to get even better data. Again, you see the iron is concentrated in the Mare very nicely here, and so we now know that we are getting data which are about a factor of 10 better than we had proposed to NASA that we would get. That is in part due to the fantastic job Bill did of building these 3 spectrometers, and secondly, the spacecraft being small, very simple, and very clean, has no background. And so we have a very clean system to work with. The alpha particle spectrometer is doing some strange things. We were at solar minimum when we launched. This is the general background. These are 12-hour integrations, these are engineering plots. This isn't science yet. But we started noticing instead of getting 5 or 8 counts per 32-second frame, we were getting sometimes many, many times that, 100 counts or more. We realized that the sun was beginning to get active, and we're getting flooded by solar alphas. This was a few weeks ago, and you can see we were getting very large count rates. And the next view graph I'm going to show you is a blow up, if you will, in time of an event which was so strong that it not only flooded the alpha particle spectrometer, but also overloaded the gamma ray spectrometer and the neutron spectrometer. And I'm beginning to be suspicious that we had some damage to the solar cells, but that's a different story. This is the normal background. We went 3.5 orders of magnitude more alphas. So we're just being bombarded. You can see the orbital period here because clearly when we go behind the moon, we see fewer alphas. So it's turning out that our alpha particle spectrometer is not only going to give us hopefully some good data about the moon. I say hopefully because when you got that kind of background, you don't know what you're going to get. But it's turning out to have a lot of good solar physics data. And I've been talking with the solar physicists at Stanford and Palo Alto, and they're very excited about these data. Now the final pair of experiments, of course, mapped in tandem the magnetic fields. And what we see here are orbital passes for the electron reflectometer and the magnetometer. These are individual orbits, night, day. And we knew from Explorer 35, which was pre-Apollo, that the magnetic fields of the moon are very, very small. But when they get right at the edge of the moon, as seen from the solar wind vector, you can get attached shocks. That is, most of you know, I believe, that the geomagnetic field holds off the solar wind. There's a bow shock, there's a magnetosheath, the magnetopole is a very interesting structure. Well, that all doesn't exist on the moon, at least we thought it didn't, because these fields are far too minuscule. But right at the very edge of the moon, as I say, just before rotation carried around, you get this little bitty shock. Well, we began to see this, and you see this here, and this is a 2-to-1 ratio, which it should be. In fact, it's a little more than that. And so we were seeing these shocks, but here the solar wind began to blow much more fiercely and just collapsed it right down. The interesting thing is, this is not the edge of the moon. This is standing right out in front of the moon. This is a detached shock. So this magnetic field complex is strong enough to hold off the solar wind most of the time. Now, the last view graph I have shows a very preliminary map, and believe me, our data analysis is going to be going over the next couple of years, so all I can show you today are initial results. But you can begin to see the structure. This is in the far side polar, South Polar Atkin Basin. We knew from Apollo that something was going on there. We know now that, of course, a lot's going. But we're beginning to then map the distribution of these local magnetic fields. So I can just give you a taste of what Prospector has begun. As I mentioned, the data quality is in all cases about a factor of 10 better than I had promised NASA. The spacecraft has been functioning absolutely flawlessly. It's a gem to fly. I keep telling reporters that a kid could fly this thing, and I'm not kidding. I could teach anybody to fly the Lunar Prospector in a couple of hours. And this is the way I believe spacecraft should be built. Not that simple spacecraft like this can do all of lunar and planetary science, because they cannot, but they certainly can do a large fraction of it. So with that, I'd like to end and answer any questions you might have. And again, I would really like to thank the NSS for supporting this effort, all the groups who did, all the individuals, because these are your data, this is your spacecraft. Thank you very, very much.
Just a brief word about the eventual impact of the lunar surface.
Oh, yes. By intent. When we go back to that plot I showed giving the decay of the periselin with time, as long as I have fuel, I will be able to maintain the orbit by correcting for that and bringing the spacecraft up. We do that once every 56 days right now. When we go into the extended mission mapping and are down at 25 kilometers, we'll actually be orbiting between 10 kilometers and 40 kilometers, because immediately the circular orbit becomes elliptical. In fact, it's surprising how fast that goes. In a matter of a day, you've changed your altitudes by plus or minus 10 kilometers. It's very, very rapid. In any case, about 7 days after I run out of fuel, Prospector will hit the moon at about 1.7 kilometers per second, which of course will totally vaporize it, which is intent. We all know of the orbital debris problem in the Earth. Every single orbiting spacecraft that's been around the moon, with the exception of Explorer 35 and one other Explorer, which are in very high orbits, have been intentionally impacted. And so the fate of Lunar Prospector is going to be that of an impact. Any other questions?
Yes.
Yes.
I noticed in your, I know there's a great excitement about the water, obviously, but your instrumentation charts did show you could find uranium. Is that correct?
Yeah, but uranium, thorium, and potassium are detectable with a gamma ray spectrometer because they give off gamma rays as part of their radioactive decay. The other elements that we see in the gamma ray spectra, and by the way, the neutron spectra, are also generated because cosmic rays hit the moon and generate neutrons and gamma rays. Now, this material creep that I mentioned, the acronym means potassium, rare earth elements, and phosphorus. These are trace elements. We call them incompatible elements because they do not fit in the crystalline structure of the more common elements which make up lunar materials. As such, they are concentrated very strongly in a magma that is cooling in the last percent or 0.5%, and you get concentration factor of 1,000 or more. Now, this is an important thing for us in terms of lunar petrology because it allows us to use it as a tracer. And we can understand mixing of impact ejecta with regolith and things of that nature. So it's a very important thing, but in terms of locating uranium deposits, that's not what we're doing.
Okay, I'm just curious. No uranium you're finding then?
Well, we haven't got down into the spectra that far. The thorium is really easy to see. It depends on its line strength. For example, it's difficult for us to measure magnesium and calcium. What you do in a spectra like that is you start to strip it. You take the most obvious lines, and there are many lines. Many of those lines are composite. They are not just, as we said, iron or something else. There'll be iron and uranium and thorium in there. And so you take out the oxygen, you strip that out and subtract it. Then you take out the iron. You take out the big things, and slowly but surely as you do, then other lines appear. We will get to uranium eventually.
Okay, we have one more here.
I'd just like to point out that uranium and thorium tracked very close together in the Apollo's moon samples. So where we find the thorium, we will find uranium here also.
I was going to ask if you are planning on continuing to use the instruments to continue to map right up until the point of impact.
Oh, absolutely. Absolutely. That's the whole purpose. The question was, are we going to continue mapping until we impact? Absolutely. I mentioned that I started turning the instruments on a few hours after launch. They are on all the time, collecting data all the time and transmitting it to Earth all the time. The last gasp will be data as we impact.
Thank you.
Couple of quick announcements. We pushed back the start of all the talks, so you didn't miss any of the start of the 2 o'clock talks. So,
All right, we just have one last thing here for Dr. Binder. We have a nice award to present to him.
We'll make this speedy because I know you all want to get on to your next talks. And as all of you know, we usually present our awards at the awards banquet on Sunday night. Alan Binder has been awarded the Pioneer Award for Scientist of the Year, and unfortunately he and Rebecca can't stay with us tomorrow. So I won't take a lot of your time giving a long salutation, because I think all of you are here at lunchtime today because of your familiarity with the mission and because of your enthusiasm for it. I will tell you that Alan comes out of a pretty famous stable. He started in astronomy, trained under Kuiper, and he was one of 4 stellar students. He did his doctoral work alongside Carl Sagan, who is actually going to be awarded posthumously a Heinlein Award for '97. Bill Hartman, the space artist who many of you know, and Dale Cruikshank, who is still very active in studies of ice in the solar system. In fact, he's working with me on a book on ice at the moment. So he had a very interesting start in space science. He also, it hasn't been mentioned here, was on the Viking lander team at a very exciting time, and worked on Mars for a long time, early in NASA's attempts at Mars. And many of you have known him since 1988, 1989. I think the first discussions at NSS about being associated with Prospector were in Chicago in '89. So it is really a great pleasure for us, Alan. I'm going to ask Kirby Eichen, chairman of our executive committee, to come up and actually present the Space Pioneer Award for Scientist of the Year for '97 to Alan Binder. And it's detachable, Alan. You get a globe, and so everyone knows there's an inscribed plate it stands on that says Space Pioneer Award 1997.
After that, I was just going to say a sincere appreciation for your vision and persistence, I think, and your recognition of the role that activists play and all of that, so thank you.
Well, I'm deeply appreciative of this honor, but I accept it only in the sense that I do represent all of you. This is not just my effort. It belongs to Gay, it belongs to Rick, it belongs to every one of you who supported this effort and believed that there is a role that we can play outside of the government. So this is your award too. It's your spacecraft, your mission, and your award, but I do accept it very humbly. Thank you very much.